Welcome to Robots That Learn and Adapt. In this episode, we explore 58 groundbreaking robotics research papers published on November 24, 2025. Our focus: how intelligent machines are evolving to generalize, operate efficiently, act safely, and learn continually. Join us on a journey through the latest innovations shaping the future of robotics. This presentation will guide you through the primary advances at the frontiers of intelligent robotics. The session begins by setting the context for recent breakthroughs, then unpacks dominant research themes observed in current literature. Seminal papers that are actively shaping the field's trajectory will be highlighted, with technical concepts explained for listeners of all backgrounds. Throughout, we will spotlight anticipated future directions and identify the open challenges that remain. Robotics stands at the intersection of mechanical engineering, electrical engineering, and computer science. The field's central ambition is the creation of autonomous systems capable of sensing, planning, and acting in real-world environments. Applications are wide-ranging, encompassing industrial automation, healthcare robotics, autonomous mobility, and planetary exploration. Current research is focused on developing machines that can adapt to the inherent complexity and unpredictability of real-world settings. The robotics section of the arXiv preprint server has become a global nexus for rapid innovation, fostering collaboration and the dissemination of cutting-edge research. A major theme emerging from recent research is the integration of vision, language, and action into cohesive robotic systems. This unification aims to enable robots to perceive their environment, understand instructions, and execute purposeful actions. Notably, the work by Fu and colleagues on MergeVLA demonstrates the feasibility of merging multiple expert models into a single generalist agent, capable of handling diverse tasks. Recent pipelines increasingly combine sophisticated visual perception with action planning, striving for robots that adapt flexibly to any task or setting. A persistent challenge within this integration is overcoming catastrophic forgetting, which can undermine the retention of specialized skills during model merging. Adaptive and efficient robot control is another central theme. Chun and collaborators propose adaptive compute scaling, allowing robots to adjust computational effort based on the difficulty of each task. This efficiency is crucial for deploying robots in resource-constrained environments, making advanced control feasible in real-world settings. Model predictive control, or MPC, remains a foundational technique, enabling robots to plan ahead and maintain safety. The development of anytime controllers is particularly notable, as they strike a balance between operational speed and task accuracy, dynamically allocating resources as conditions change. Continual learning and the concept of robot-powered data flywheels are transforming the way robots improve over time. Grannon and colleagues have demonstrated that robots can autonomously collect and label data during deployment, facilitating ongoing adaptation without extensive human intervention. These data flywheels effectively close the gap between training and deployment, allowing robots to refine their performance in real time. Modular data management platforms now support efficient, ongoing data collection and model adaptation, emphasizing self-supervision and minimizing the need for manual annotation. Safety, trust, and the nuances of human-robot interaction are becoming increasingly prominent in robotics research. Real-time safety verification frameworks, such as the Guardian system, enable trustworthy operation in brain-controlled assistive robots. Protocols are being developed to ensure both the physical and psychological safety of human-robot interactions. Human-in-the-loop learning, incorporating feedback, teleoperation, and direct brain interfaces, facilitates more intuitive and safer collaboration. This evolution emphasizes a shift from robots as mere tools to robots as collaborative partners. Recent findings position robotics at the edge of adaptability. The MergeVLA system, developed by Fu and colleagues, achieves generalist robotic agents that match or surpass the performance of specialized experts. The DASIP framework by Chun and team reduces computational requirements by up to 4.4 times while maintaining robust performance. Grannon's Scanford robot, deployed in real-world library settings, demonstrated that autonomous data collection can double accuracy rates. Safety frameworks are now enabling reliable, user-centered robotic systems, while modular and continual learning strategies are driving scalability and relevance across varied domains. Several methodological advances underpin current progress in robotics. Large-scale pre-training and transfer learning techniques facilitate generalization across tasks and environments. Model predictive control is widely used to ensure robots move safely and consistently by planning actions based on predicted future states. Hybrid system architectures combining high-level reasoning with low-level control are enabling more flexible and robust performance. Neural network approaches are increasingly employed to model both perception and robot dynamics. Additionally, human-in-the-loop systems leverage user feedback and intent, resulting in more adaptive and responsive robots. The MergeVLA paper by Fu and colleagues presents a seminal advance in generalist robotic control through modular merging. Entitled MergeVLA Merging Multiple Expert Models into a Generalist Vision Language Action Agent for Robotics. This work addresses catastrophic forgetting, a key barrier to merging expert models. The modular architectural design supports scalable, adaptable multitask robots, setting a foundation for continual learning and skill composition. Across multiple benchmarks, MergeVLA is shown to match or even outperform specialized agents, confirming its significance for the future of generalist robotic systems. June and collaborators introduced the difficulty-aware stochastic interpolant policy, a pivotal contribution to dynamic compute scaling for robot controllers. The paper titled Difficulty-Aware Stochastic Interpolant Policy, Dynamic Test Time Compute Scaling and Control Policy, justifies adaptive control as a means to conserve computational resources without compromising robustness. The framework enables deployment on hardware with limited resources and supports real-time operation. By introducing a difficulty classifier for real-time compute adjustment, DSIP has a significant impact on the development of efficient, anytime robotic control systems. Grannon and her team present robot-powered data flywheels, deploying robots in the wild for continual data collection and foundation model adaptation. This paper demonstrates how robots can autonomously gather, label, and utilize new data in real-world environments. The Scanford robot, deployed in a library, doubled domain-specific accuracy and improved optical character recognition benchmarks, all without requiring manual annotation. This approach paves the way for scalable, self-improving robotic systems, capable of continual adaptation and learning from real-world deployment. Looking ahead, several future directions are emerging within robotics research. The evolution of foundation models is expected to produce increasingly adaptable robots, capable of handling diverse tasks with minimal retraining. Real-world continual learning, supported by open-source data platforms, will facilitate ongoing adaptation and improvement. Modular and merging-friendly architectures will be crucial for scalable skill composition. The expansion of human-in-the-loop and brain-computer interface paradigms is anticipated to enhance accessibility and safety. Throughout, safety and trust will remain central pillars, ensuring public acceptance and responsible deployment as robots become ever more integrated into society. This analysis was synthesized using advanced tools such as GPT-4.1 from OpenAI, Deepgram TTS, and OpenAI image generation technologies. All content has been reviewed by human experts to ensure clarity and accuracy, though minor oversights may persist. Every referenced paper is cited within the analysis. AI tools have enabled a rapid and cohesive review of 58 research papers, reflecting a commitment to transparency and continuous improvement in presenting complex technical advances. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.